All right, so let's start today's lecture. So in this lecture, I'm going to solve a few more problems from chapter 5, but most of the problem, and I think all the problems are basically based on the concept of the gravitation and the satellite. Okay, so the first two problems are very easy. Actually, yeah, very easy. And then we have few little bit complicated problem. Okay, the first problem, this one, number 9, is easy. It asks us to calculate the gravitational force given that we have two objects and the distance between the two objects. Okay, so the equation we need is this equation to solve this problem. The gravitational force is equal to the universal gravitational constant times m1 m2 divided by r square, where m1 and m2 are the masses of the two objects and r is the distance between them. And if the objects are small, then it doesn't matter whether you are measuring the distance from the center or edge. But if it's a big object, for example, when we are dealing with planet or some big object, we have to determine the radius, I mean the distance from the center of the object. Okay, so for this problem, because the objects are small, so it doesn't matter. So let's plug the values. All the values are given, so let's plug the values and then determine what is the gravitational force. So the value of the gravitational constant, universal gravitational constant, is this: Newton meter square over kilogram square. And then 65 kilogram is one person's mass and another person mass is 50 kilogram, and the distance between these two person is 2 meters. Okay, so square, make sure you also use the square sign. Okay, so when you plug all these values, you should get this value. Okay, it's a very small number. So although there is some attractive force between your instructor and you when you are in person class, but we don't feel it. Okay, you don't feel it because the magnitude of the force is very small. Okay, that's why we don't feel. But in reality, there is some force that attracts between two objects in this universe. Okay, in many cases we don't feel it because of the small magnitude. Okay, all right, then this problem is also very similar. Number 10 is also very similar. Here we are going to measure the force, the gravitational force between the satellite and the earth. Okay, now here you see that the satellite is 6380 kilometer from the surface of earth. Okay, but because earth is a very big object, okay, so we have to measure the distance from the center of the earth. So when you have a big object, something like this, make sure you plug the distance you use in the equation measured from the center of the object. Okay, so again the equation is this one: Fg equal to the gravitational constant r square, m is the mass for satellite, and m is the mass for the earth. Okay, now here again this is 6.67 times 10 to the power minus 11 Newton meter square kilogram square. The mass of the satellite is 2000 kilogram, it's given. Mass of the earth is 5.98 times 10 to the power 24 kilogram, it's also given. Now here we have to be careful. Okay, what is this distance? Okay, so this is 6380. Okay, and also this is 6380. Okay, so that's why the total distance from the center of the earth to the satellite is 2 RE. Okay, so we have to the square of this distance. Okay, so what is this distance? This distance is, let me write down, 6380 kilometer square. Okay, now kilometer, you have to convert kilometer to meter, because kilometer is not standard unit, so we have to convert it in meter. Okay, so this factor we need. Okay, so 2, because from here, from the center to the satellite is twice the radius of earth. Okay, for this problem. Okay, all right, so when you plug all these values in your calculator correctly, you should get something like this, 4,900 Newton. So the force is 4,900 Newton, and this is reasonable. And if someone is pulling by pulling you by this force, you will feel this. Okay, so I mean, this is a very big number. So the earth attracts the satellite by this force. Okay, all right, let's move on. All right. All right, so what is the value of the next problem is, what is the value of the gravitational acceleration 400 kilometer above the Earth's surface, where the International Space Station is in orbit? So it's basically asks us to calculate the gravitational acceleration at the International Space Station. Okay, now if you remember, we derived an equation for the gravitational acceleration, and that was something like this. G, the gravitational acceleration, is equal to universal constant, the mass of the earth, and then R square. Okay, so this R square is again the distance from the center to the, from the center of the earth to the satellite. Okay, it's not the radius. Okay, remember that. Okay, if it is on the surface of earth or on the surface of the planet, then you can use it as the radius. But because 400 kilometers is a significant number compared to the radius of the earth, so you have to be careful here. Okay, so this is 6.67 times 10 to the power minus 11 Newton meter square per kilogram square, and then mass of the earth is 5.98 times 10 to the power 24 kilogram. Okay, and R, here we have to be careful. R is, so if you remember, the radius of the earth is 6380 kilometer, and the International Space Station is another 400 kilometer. Okay, so from the surface to here where the satellite is, it is 400 kilometers. So R will be these 6380 plus 400 kilometer. Okay, 6380 kilometer plus 400 kilometer, and then square. Okay, now again, kilometer is not standard unit, so we have to convert both kilometer into meter, and we need this factor. Okay, so we need this factor. So try to understand how we did. Okay, so kilometer to meter means 1 kilometer means 10 to the power 3 meter or 1000 meters. So we have to multiply it by 1000 or 10 to the power 3 to convert from meter to kilometer to meter. And then you see we have square here. So then if you plug this equation into your calculator, it should give you this value. Okay, so you see that in the space station, which is 400 kilometers from the surface of Earth, okay, the acceleration is lower than 9.80. Okay, so the acceleration of gravity due to due to Earth's gravity inside the space station is 8.68 meter per second square. All right, now let's use the same equation to determine the gravity on the moon. Okay, so again it is this equation. All right, so the equation is this, again the same equation, but now because we are calculating the gravity of moon, so we have to change it. Okay, the mass of the moon, and here we are basically interested on the surface of the moon. Okay, so what is the value of gravity on the moon? On the moon means basically on the surface of the moon. So here we can basically use the radius of moon. Okay, all right, so it's simpler than the last one. And the mass of the moon is this 7.35 times 10 to the power 22 kilogram, and then radius of the moon is 1700 kilometer. So kilometer means 10 to the power 3 meter, and then make sure you use a square. Okay, and then plugging all these values into your calculator correctly, it should give you this value. Okay, so the acceleration due to gravity on the surface of moon is 1.60 meter per second square. Okay, it's about 6 times smaller than Earth's gravity. Okay, all right. The next question, number 13, asks us to calculate the orbital speed and period for the International Space Station. Okay, now here, if you remember, so let me erase. So in the theory class, we derive an equation for the orbital speed of a satellite. Okay, so if you remember that equation, it was something like this: v orbit equal to square root of the universal gravitational constant, the mass of the Earth, and then the distance. Okay, here this is just the distance. Okay, so this is the equation for the orbit, the orbital speed. Okay, now plug the value. So this value is constant. Although in this question there is I didn't give you any number, but you can get all the numbers from question number 11. Okay, so this is known value, right? This is a constant, and then mass of the Earth is 5.98 times 10 to the power 24 kilogram. That is also known value, and these are, you have to be careful. Okay, so 6380 kilometer plus 400 kilometer. Okay, so this is the distance of r. Okay, but again, similar to the problem 11, we have to convert this into meter. Okay, so this is in meter. So now it is a correct number. So if you plug all this value and then square root, you should get the speed. Okay, and the speed of the International Space Station is this. Okay, so here we assume that the International Space Station orbits in a circular orbit. Okay, but in real life, it's not orbiting in a circular orbit, it's in elliptical orbit. So so this is not basically the real speed. Okay, but it's very close. Okay, now the next question is what is the period? Okay, so you find the speed, what is the period, and again remember that we already know how to create how to calculate period. So period for this problem, we can use this equation, right? So the distance, the speed is distance divided by time. So in one full turn, the satellite travel this distance, and the time needs equal to the time period. So by solving these, we can find the time period. Okay, so for time period we have a complicated equation, so but we don't need that complicated equation for this problem because we already know the speed. Okay, so this is the simple equation we have, I mean, we should use. I mean, it doesn't mean that using the complicated equation you cannot determine the time period. You can, but this is the easiest way. Okay, all right, so 2 pi r is this 2 pi, but r should be this 6380 times 10 to the power 3 plus 400 times 10 to the power 3. So this is r, and v orbit is 7670 meter per second. Okay, so if you plug these two values, I mean these values, into your calculator correctly, it should give you this number, 5389 second. Okay, if you want to calculate it in minute, you have to divide it by 60. Okay, and I got about 90 minutes. Okay, so what it means in every 90 minutes the International Space Station orbits our Earth. Okay, so you know that in one day they orbits our Earth 15 times. I mean, approximately 15 times. And yeah, I mean, it's very close. I mean, I remember that. I mean, from an article that the International Space Station orbits our Earth 15 times in one day. So, and this simple equation basically shows these. Okay, so the speed we calculated here is basically very close to the real speed of the International Space Station. Okay, all right, so we have two more problems. So number 14, and then a problem about the geostationary satellite. Okay, so what number 14 says that determine the mass of Earth from the orbit of the moon. Okay, so so here we do not have much information, but what it what we can use is this equation. So one of the equation we derived was this 4 pi square. At the end we derived this equation. Okay, so the time period is related to the distance r and the mass of the earth. Okay, so let's say here is the earth, here is the moon. Okay, and the distance from the earth to moon is 3.84 times 10 to the power 5 kilometer. Okay, so let me write it in meter. So it would be 3.84 times 10 to the power 8 meter. Okay, because kilometer to meter is another 10 to the power 3. So 10 to the power 5 and 10 to the power 3 added together to 10 to the power 8 meter. So this is the r. So r here is this one. And t is, in one problem we use t for the moon is 27.3 days, right? So it is basically 27.3 times 24 hours. In one day there are 24 hours, and then in 1 hour we have 60 minutes, and in 1 minute we have 60 seconds. So the time period is basically this. Okay, so if we know r, if we know t, we can easily calculate the mass. Okay, so that information, although it's not given in the question, but we can use this information. Okay, so because we have to calculate the mass of earth, so let's solve this equation for this mass of earth. So it would be, okay, so now here if I plug the value of r, and a universal gravitational constant and the time period, okay, then what I find is this number. Okay, so although we use this information, and what we get is very close to the real mass of the earth. So if you remember, in many problem we use this number for mass of earth, 5.98 times 10 to the power 24 kilogram. So this is very close to this. Okay, so by using this equation, the time period equation, you see that you can determine the mass of earth, and that is very close to the standard value. Okay, all right, now the last problem. The last problem is about the geosynchronous or geostationary satellite. Okay, so it asks us to calculate the height of the geostationary satellite. Okay, so let's say here this is the surface of earth. Okay, we have to basically calculate this distance for the first one and the speed. Okay, I'm not going to do this one. Okay, so just let's do the first two, the height and the speed. Okay, all right, so to solve this problem we can start with the same problem that we used in the last problem. Okay, same equation that we use in the last problem. So this is this 4 pi square g m e r cube. So it asks us to calculate this distance, okay, from the surface of Earth. So surface of Earth is somehow related to this quantity r. So let's first calculate r, and then from r we can determine what is the distance from the surface of Earth. R means basically, this r means the distance from the center of Earth. Okay, so here you have to remember that. So if I solve this equation for r cube, it gives me something like this. Okay, so then plug the value, all the known value. Okay, g is 6.67 times 10 to the power minus 11 Newton meter square, kilogram square. Mass of Earth is 5.98 times 10 to the power 24 kilogram, and then 4 pi square is that, and t is 1 day. 1 day is 24 hours. 24 hour means, I mean, is 24 times 60 minutes, and 60 minute, I mean 24 hours 60 minute means this much second. Okay, so because we need the number in second, so we have to calculate, I mean we have to multiply 24 hour with 60 for minute and 60 for second. Okay, so this is the equation, I mean this is the numerical equation. Now if you plug all this value in your calculator, it will be giving you a very large number. Okay, so I don't even know, so it's not written in my note. Okay, so what I have is, so let's say we get some number. Okay, so I don't know what is the number, I don't have this number here. Okay, I have the final number. So you see that what we calculated here is the cube of r. So what we have to calculate is r. Okay, so to calculate r from r cube, we have to do cubic root. Okay, so this is the number, and then we have to do cubic root. Okay, so in your calculator, find this operation. Okay, it's not the square root. Okay, the square root is just a simple root, but to do this operation you have to find this operation. It's not, I mean sometimes it's not there, so you have to probably use the inverse mode and then find these. Okay, so the cubic root of the equation, the number you calculated here, and basically this number, what I got is this. Okay, so 4.23 times 10 to the power, so 1 2 3 4 5 6 7, so 7 meter. Okay, so these are basically the distance of the satellite. Okay, distance of the satellite, I mean the geosynchronous satellite, from the center of the Earth. Okay, yeah, and the time period, you know, the time we use this time period because for geosynchronous satellite the time period is 1 day, so that's why we use this one. I forgot to mention earlier. Okay, and this radius, I mean this not radius, this distance r is from the center of the Earth, but the question asks us to calculate the distance from here, from the surface of Earth. So what we have to do, we have to subtract the radius of Earth. Okay, so the radius of Earth is 6380 kilometer, right? Kilometer means 10 to the power 3 meter. So what I got after subtracting, I got something like this: 3.59 times 10 to the power 7 meter. Okay, so if you subtract this, the radius of Earth, from this number, you get this. So it's a large number. Okay, so normally geosynchronous satellite has to send a distance of 3.59 times 10 to the power 7 meter from the surface of Earth. Okay, all right, the last problem in this chapter is the what is the speed. Okay. So, all right. So we know the time period, we know the radius. Now we have to calculate the speed. Okay. The speed of the geosynchronous or any satellite is easy to calculate because we know that orbit equal to 2 pi r divided by the time period. Okay. And the 2 pi r is basically this distance, not this distance. Okay, don't make mistake here. So r is basically the distance from the center of the earth to the satellite. So it is what we just calculated, 4.23 times 10 to the power 7 meter. And the time period for a geosynchronous satellite is 1 day. 1 day means this much second. And if you plug this value correctly in your calculator, you should get this speed. Okay. So you see that this is lower than the space station's speed. The space station speed, I remember it was 7,600 meter per second. Okay, it's less than half even. Okay, so what it means as it is going away from the surface of the earth, the speed decrease. Okay, close to the surface of earth, I mean, when the satellite is at around 400 kilometer, you see that the speed is 7,600 meter per second. Now it is far from the earth. Okay, it's about like a 35 or 36,000 kilometer. Okay, so you see that this is 36,000 kilometer. Okay, it's far from surface of earth. So as it is far from the earth, okay, the speed is less. All right, so we are done with this chapter. So in next class we are going to start a new chapter, chapter 6, and it is about work, energy, and power. All right.